Okay, fine. Okay, I started recording, right? Okay, fine. So, Arvindo, what is your last class? Hello? Arvindo, what is your last class?
Ridge regression.
Ridge regression, right? Okay. So, let me go for open my documentaries things. You guys are able to access the recordings, right? Recordings as well as documents as well, right? Okay. So, yesterday we started giving explanation about regularizations. Yes or no? So what exactly the regularization? Okay, so regularization is a technique. It can help you to preventing the overfitting by adding the some kind of penalty term to the objective function. So here objective function means your cost function or error function. Okay, so our goal is the goal of the regularization is to reducing the magnitude of model parameters, so which help you to preventing the overfitting and improve the generalization of the model actually. Okay, so here the regularization can be applied in a different type of models, including like we can apply this kind of regularization to your linear regression, logistic regression, as well as neural networks also. Okay, there are two type of regularization concepts are there or techniques are there. The first one is the L1 regularization and second one is the L2 regularization. Let's talk about the L1 regularization. So the L1 regularization, we have another name is lasso regression. Okay, L2 regularization means it could be ridge regression. There are two type of regularization concepts are there, L1 and L2. The another name for L1 and L2 are lasso regression and L2 means ridge regression. Okay, so here here the hypothesis function could be same for the lasso and ridge, but the objective function can be a change. The objective function, we need to go for add some absolute values of the model parameters that we are calling it same.
Hello, sir.
Hello? Yes, tell me. Hello? Hello? Yes, I can hear you, but you are mute.
Yeah, I was not able to hear you. That's why.
Now
Okay.
you can able to hear me, right?
Yeah. That's okay.
Guys, now you can able to hear me, right?
Yeah, we've been hearing you. Yeah.
Okay. So nothing I'm explaining. Yesterday we just explained only ridge regression. Now I would like to complete the lasso regression as well. Okay. Here lasso and ridge both are used for to preventing the overfitting when you're applying the or when you're building the machine learning models. Clear? So now, so here we are talking about the lasso regression. Lasso regression means we are just adding the some kind of penalty term to your objective function. So here the objective function is to be minimized becomes the sum of the squares of errors plus lambda times of the sum of absolute function. You just see this particular formula, you will able to understood actually. Okay, see, objective function means sum of errors plus lambda into sum of absolute values of the coefficients. Okay, so some square error means it's 1 by n into sum of your actual minus your hypothesis function. This is the function we are calling it say hypothesis function. Let's take this thing h of x I h of x. Okay, so h of x means your actual hypothesis function. Okay, this is your predictor or y hat. You can simply say that y predictor or else hypothesis function. This is the thing we are calling it same. H of x equal to, okay, so this is the thing we are calling it, say, your linear regression. Okay, this is the equation of the linear regression, right? Okay, or else we can simply say that it's your y value. Okay, and so a of I, simply you can consider predictor value. Okay, so h you can consider as the h, right? No. Okay, fine, simple thing, guys. So this is the objective function. So the objective function of the linear regression, this one only, but we are adding some extra penalty term that it could be lambda into some absolute values in the sense absolute value of the parameter 1, absolute value of the parameter 2, absolute value of the parameter 3, and so on. So when you do that sum of this thing, that we have to multiply it with this lambda value. This lambda is your hyperparameter value. Okay, so that's what I am trying to be explaining here. So objective function to be becomes the sum of squares of. Someone is joined with the name of Chitra. May I know?
Hey, actually, this is me. I was on my phone and my laptop isn't working, so I'm just joining through my other laptop. Sorry about that. That's me, Chitra Shekhar, joining through the other laptop. Shalini here.
Okay,
I will disconnect here on the phone. Yeah, sorry about that.
Okay, fine. Cool enough. Okay, so we are talking about objective function, right? So the objective function now here, this is the effect of shrinking the model of the parameter towards the zero. Okay, so which can be useful in case of where are the many features, when we have a more features and some of the features are highly correlated or irrelevant. So those things we can handle it. L1 regularization will give the sparse solution, as it will make some of the coefficients become zero. So when it is useful, which is useful for feature selection. So we would like to make it some kind of coefficients to zero by the time. So only important features we are going to be selecting with help of the lasso regression. So with help of the lasso regression, we are not only minimizing the objective function or cost function, we are going to be selecting the features, important features. I think this L2 regularization I already explained. So ridge regression, we are calling it as a L2 regularization. Here the objective function is we should minimize, and minimize becoming the sum square error plus lambda times lambda, you have to multiply it with sum of the squares of the model parameter. That means sum of squares, right? Okay, you can see this formula. You just see this particular formula. This is the sum of squares. Okay, your parameters. Okay, we are doing the square and we are doing the sum, but previously we are doing the sum, but we are we are absolute sum actually, but this is square sum of the parameters, and this is absolute sum of the parameters. That is the difference between the lasso and ridge regression. Okay, clear? Can see, we just read this one, you can easily understand what exactly this one is. Okay, lasso regression is a type of linear regression that uses the shrinkage, which is the process of reducing the magnitude of estimated coefficient, and it is the regularization technique that adds the penalty term to the linear regression objective function. The penalty term is absolute value of the coefficient multiplied by the lambda value. So here the lambda is the hyperparameter. Okay, it will be controlled by the user only. Okay, that controls the strength of the regularization, and that lambda value we can fix it our own way. Okay, I mean, as you require, you can able to fix it. The objective function of this particular lasso regression is sum square error plus lambda into some absolute value of the coefficients. So this is the SSC and sum of the absolute coefficients. So here n is nothing but it's a total number of observations, and y is the actual values and of the response variable of the ith observation, and xi is the ith observations of the predictor variable, and here the b0 b1 are the coefficients of the linear regression model, and the lambda is the regularization parameter. Okay, so minimizing the objective function will shrink the coefficients towards 0, and some of the coefficients becomes 0. That means that coefficients, that beta values, it was very small, and sometimes it was 0 when it is unuseful for us. Okay, the lasso algorithm will select the only subset of the features setting other to 0, which is why it is useful for feature selection. So some of the things, if you're not interested, that means if it is not important, where simply coefficient you are put as a 0, then my linear regression can be changed. Okay, so here L1 regularization term, absolute value of the coefficient as the effect of shrinking of the coefficient towards 0, which can be useful in the case of where there are many features or some of them highly correlated or irrelevant. The L1 regularization term will give the spare solution as it makes some coefficients become 0, which is useful for the feature selection. Okay, this is the hypothesis function for the lasso regression. See, this hypothesis function or linear regression could be same for the multiple linear regression only. Okay, so here multiple linear regression and ridge regression, lasso regression, the hypothesis function could be same, but the objective function, the cost function could be differ. Okay, and that too, the objective function, the cost function of the multiple linear regression and lasso and regression almost same, but we are just adding some extra penalty term. Clear? Clear or not? So this document I can provide you guys, and it will help you for interview perspective as well. Okay, now we'll do a small program or project so that it will help you to understood that ridge and lasso regression in. Okay, lasso and regression, and so here we have some kind of housing.csv. This is my data set. Okay, I would like to go for predicting the house price with help of the multiple linear regression, but maybe it may be overfit, so that we can overcome with the lasso regression and ridge regression. This is could be requirements, and maybe these are the libraries we are going to be using. Okay, let me go for open the your lasso regression, sorry, your Jupyter file. So my Jupyter file is, first we need to go for importing the libraries. Okay, important libraries. This train test split is the method we need to import from the scikit-learn, and this scikit-learn, which we have the model selection module, from the model selection module, and we are going to importing the function is train test split, and we have the linear model is the library or module of the scikit-learn package, and inside of it, if you want to do that linear regression, we have to import the linear regression class and lasso regression class and ridge regression class. Okay, with help of this predefined classes of the linear model, we can able to go for build the objective of or object of the linear regression, lasso regression and ridge regression. Okay, so here we have the matrices. Here we are just having the mean square error, but we have a lot of matrices. We have it, that all matrices we can able to go for use it. Mean square error, root mean square error, R square error, and absolute root R square. Okay, AIC, BIC values, lot of things we have it. Those are all matrices. Okay, with help of the matrices we can able to go for validate your model. So this is the thing why I imported the Google Drive here. If you want to mount, so this is the folder which we have the your Jupyter file and your data set. If you want to mount this data and these files, if you want to mount or if you want to access this CSV file into my Google, okay, make sure that we need to import this Google Drive, and then after you have to mount this one. When you mount it, we can able to access the data from the, or we can able to access anything from your Google Drive into your program. Clear? Clear or not? Okay, let me go for the import the all the libraries. Once if you import the libraries, it will ask you which Google Drive should I need to be connect, and I would like to go for connect this Google Drive only. If I give the allow option, I can.
For this first, we have to upload data .csv.
So actually, if you're working with your local machine, this statement is not needed. Okay, but my data set was available in my cloud drive. So if you want to access this one, I would like to go for use these two statements in my program. Clear?
Okay.
So if you mount your drive, then I would like to see this is the housing.csv file which is available in my drive, and inside of the my drive I have the mac underscore engine, and inside of the mac underscore engine we have the ml, and inside of the ml we have the las or underscore versus ridge and main, we have it, right? So this is the library, or else we can rename this one. And if you rename, just for understanding purpose, I'm just rename this one. Okay, after you rename this one, I would like to go for execute this one. It will throw me an error. The error is the column, or the name, column name is not defined. Okay, so that means this is the thing we are not defining. Okay, even though you can able to remove this one. Okay, columns a variable you define, even though you are getting the file not found error. Okay, the reason is that in this one we have the lasso underscore vs underscore ridge, but unfortunately here this housing inside of while you're reading ml, and inside of the ml lasso underscore vs ridge hyphen main is there. Okay, that's the reason we are getting an error. Now what I should do, we can able to go for okay, remove that main under hyphen main, then we can run this one. It will able to go for returning the data, right? See, actually you are headering, you are off the header. Okay, so simply what I should do, I don't need this statement, let me remove it. Okay, by default it could be add. So instead of head of 100, I just give you 5 only. Now I can comment this one. Now I don't need this thing, because of you don't need to mention the column names. So but if you not mention the column names, header on, header true, so the headers which was not there, the names which they are not provided, that's the reason you have to be mention it. So now what I should do, I could just give that head of 5. It will display the only first 5 records. Okay, or else, okay, head of 5. Now we can just go ahead this one. So we are just displaying only first 5 records. So this is the way you can able to read the data set from your location. After that one, so here I would like to go for I would like to predict the MEDB. So why MEDB in the sense, maybe my project recruitment or my project prediction.
Your volume all of a sudden went low.
MVDB. Okay. Hello.
Yeah, better now.
Yeah, so I would like to go for predicting the MVDB, so that I'm taking this one as the my target variable, and rest of the features like CRMIM and ZN, Indus, JHS, NYSRM, Age and DS, RAD and tax, and Patricio and B and last stat. These are all things I'm taking as the X variable, features variable. Okay, so I'm taking this target variable, I'm taking it as the Y, and rest of all things I'm taking as the my X data. Okay, then if we have X data and Y data, then I would like to go for creating the train data and the test data. So if with help of the train test split method, we're just giving that X data and Y data, we are just providing that X data and Y data, and if you mentioning the test data is the 0.2, which means that it's a 20%. If we have the 100 columns or 100 observations, out of that one, 80 records are the training data and 20 records are the test data. It was considering in such a way. So that's the reason I am just taking this, I'm importing this data. Okay, and 402 records are my train data, and 102 records are my test records. This is the way we are going to be displaying the shape of it. Okay, now I would like to go for apply the linear regression. Once if I apply the linear regression, see my linear regression object, first I would like to go for creating the linear regression object, and with help of the fit function, you're training the model. Okay, so this statement, what it is doing, okay, creating the linear regression object, So once if we creating the linear regression object, and with help of the fit, and we are training the model, we are training the algorithm, LM algorithm, okay, linear regression LR algorithm. Okay, so once if you're training the LR algorithm, then what I can do, I would like to go for predict, or else we can go ahead with, we can finding the score matrices all values with help of the okay. So I can comment this one. First I would like to show you what could be that things we have it. Okay, once if you fit your model, okay, once if you fit your model, you're creating that linear regression, right? So I would like to be print that what are the coefficients we have it, linear underscore ridge dot, okay, here we have this COEF, right? This COEF values, which is printing the all coefficients, and so you just you can able to go for print these coefficients. When you print this coefficient, this is B0, B1, B2. Okay, this is B0, B1, and B2. See how many things we have it, 1, 2, 3, 4, right? And 4 into 4, it's 4 into 3, it's a 12, 12 plus 1, it's a 13, right? Okay, how many number of features we have it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Clear? So the coefficient of this CRIM, this is the first one, and this is second coefficient, like ZN coefficient, INDUS coefficient. This is the way we can able to go for print the coefficients or parameters, model parameters. So model parameters. Okay, these are the model parameters, right? This is B0, B1, B2, B3, and those things we are calling it some model parameters. And I want to print the model coefficient. Model coefficient mean your constant. Model intercept, intercept. So what could be the intercept? linear regression dot intercept. Here we have intercept underscore is there, which can be printing the intercept value. Okay, this is your intercept, like y equal to mx plus b, right? This is the b value, and this is each and m0, m1, m2, m3, something like this. Okay, so people can representing with that function like y equal to b0 plus b1 x1 plus b2 x2 plus b3 x3 plus b4 x5 plus b3 b5 x5 plus b6 x6, right? In the same way, this is your b0, this is your b1, this is your b2, b3, b4, and so on. Clear? Clear or not?
Clear.
Okay, now linear regression reg dot. So this is the score. This score function, it will you have to provide your x values. So how we can use this one? Array n sample fitted r square value, it can be written it actually. Okay, so okay, your y true, x any, y any, sample weight, x train and y train. Then the coefficient determine the r square value. Okay, we have to provide the data over there. Okay, anyway, so let me go for the printing this mean square error, and this mean square error, it will take the your y predicted values and y test values, then you're going to be printing the mean square error value with the test data. Mean square error with test data. This is error term, this is the variance, simply this is the variance. Okay, so this is the variance, right? So this is the coefficients you are already printing, so that I can able to remove it. I don't need it because of you're removing it, right? See, if I take the some kind of lambda values, this lambda values we can fix it our own, right? So after you creating the linear regression, our aim is that we have to reduce this mean square error. Okay, we have to reduce our mean square error. Now my mean square error is 20.86. I want to reduce this one. If you want to reduce this one to your mean square function, we should add the lambda into, it's a lasso. If I am using the lasso regression, then we have to multiply with the lambda into your sum of the absolute parameter. That means these are the parameters, sum of absolute parameters. Okay, for example, if I am taking the lambda value is the 0.00001, and maybe if I'm taking the you might able to take that lambda value 0.001. okay, these are the multiple lambda values. Okay, if I'm considering the you don't know what is the value we should use it. That's the reason I would like to go for the hyper parameter. Okay, I'm taking the some kind of multiple lambda values. I can train with the your data with different lambda values. Then what happen, we'll see. So we are taking the multiple lambda values for each time, which is taking the first value, and we are training, or you are building the lasso regression with this value for first iteration. For first iteration, we are building this model, and then we are fitting your text with help of the x train and y train. We are fitting the model. Then
Here that lasso on that second line, is that like the function?
yes, this is the this is the class.
Yeah, that one. Oh, that's a class. Okay.
predefined class. Okay, this is
Okay.
created. This
Okay.
is the lasso regression class, which is
Okay.
taking the lambda value and which is creating the object, lasso regression object. To this object, we should call the fit method. This fit method, which takes the X train data and Y train data, this is the way we are building the model. Okay. Once if we build the model, then I would like to go for use this lasso regression for prediction purpose. If I'm giving the some new inputs, I might be getting the Y predicted values. This is my predicted values, and Y test values are actual values. If I'm providing the Y test actual values and predicted values, then I can able to go for printing the mean square error value with lasso regression. I am taking the multiple lambda values so that I'm getting this many mean square errors. So these are all mean square errors. It could be smaller than this test data or not. See, if I'm using the simply linear regression, my mean square error is with the linear regression, it's a 20. It's a very high. But when I'm using the lasso regression, I'm reducing the my lasso. I'm reducing the my objective function or not. Okay, I'm reducing my objective function, right? And when I'm using the objective, when I'm reducing my mean square error value with help of the lasso regression for different one, from that one, the best one I can consider it. See, which is the mean square error value. It could be very small, that I'm going to be finalizing it for this situation. That means this is the lambda value. So I'm just taking my lambda value is a 0.2 and corresponding regression coefficients. That means my first 0, that means this is the feature is not important. This CRIM is not important. That's reason which is setting 0. Okay, so which is also 0, which is also 0. If something is set 0, which means that that feature is not important for you. That feature is not important for you. So you can able to go for build this methods. You can able to go for build one. You can use this one 1 2 3, okay, 4 and 5 and 6 7 and 8. Instead of training with 13 features, we can go ahead with this 8 features. So this 8 features are you already know that what columns we have it. I would like to go for print the column names, right? I would like to go for print the column name. Oh, I'm just what name we have it. Okay, I'm not trained at it. That's what we are getting an error. Okay, now we can go ahead. Oh. Okay, so here
No,
some
I
people.
have a question. I didn't catch that part. So you're trying it with so many lambda values, like minus 0, 0, 0 and all that,
Because
right?
of lambda is not constant forever. Okay,
Yeah.
so
So we are
it's
testing
the
with so
over.
many, and then oh, okay. So we are seeing which one is the lowest.
Yes,
Okay.
which one is the lowest and the corresponding lambda value, I'm going to be finalizing it. Okay.
Okay.
So this is the 80.86 and 80.87 and sorry 20.21, 22, 25, right? Here we have the 20.86. This is the value. It could be nothing value is the most of the value. Even mean square error value, it is not even smaller than this one. You don't bother about that actually. Okay, so our aim is that we have to go for predicting the best feature. We are going to be overcome the overfitting problem as well as important features. Okay, so my important features are so here this 2 are 0. We just see here this 2 are 0. That means fourth and fifth.
But this is using which lambda value? Because we gave so many lambda values, right, on the top. So for which lambda value is it giving this coefficients?
So if you want to know that one, what we should do after that one, we have to build new model. Okay. This is the last value. This is for last values. Okay. If you want to know this one, what I should do, I have to go for train with that specific. Okay, so what is the lambda value I should consider here? So which is the thing is the small from this all? Which is the thing is small? My
The
lambda value is
first one, right?
first one. Rest of all, it could be, there could be smaller high value we are getting. Okay, so I'm just taking this is the thing I'm taking as the lambda value, and I would like to go for build the model, and I fit that thing, and I would like to go for see, those are the things I'm considering it. Okay. Yep. Okay. So this is the way you can able to go for use the lasso regression. Okay. Now let's go for understanding the ridge regression. If you go for understanding the ridge regression, okay. So here also we are taking the same thing. We would like to take the multiple lambda values, and we are trying with different lambda values with the same train data, and we would like to go for take that lambda value and mean square error values from this all, which is the thing is very small that I'm going to be considering it. Okay, and it could be the first things. Actually, this is the way we can able to go for using the lasso regression and ridge regression. Okay, so we cannot come up with this only these things which is the best fit model. Okay, we have to do lot of other operations, like we have to go for use lot of matrices, and we have to we have to met all assumptions are correct or not. That all things we should do. I think you already know it, right? When I'm explaining that when I'm explaining the linear regression things, we have some kind of assumptions, that all assumptions should be applicable to lasso regression as well as ridge regression also. Okay, so I already explained about lasso regression, ridge regression, and whether it is I already explained about multiple linear regression. There we have some kind of assumptions. This all assumptions are met or not, we have to check with that one. And meanwhile, we would like to go for evaluate the model based off on your R square value, adjust R square, mean square error, and roots mean square error, and AIC BIC values. Okay, with help of those things we can able to go for finalizing our model. Okay, and here we have a VLSA model is there. VLSA regression Python. We can ordinary least square. This is the directly we can use this method as well. I'm just trying to go for use that method. Okay, so I'm just importing this method. Okay, sorry, I'm going to be least square VLSA method, and we would like to go for train your data. And first of all, you should go for add the constant. Okay, so add the constant. So what should I need to add it? Xtrain, okay. Then after we are adding the constant. After that one, we need to train your model. Okay, and so here ytrain and xtrain, then results. So we have to go for print the summary of that particular results. So this statement will give you a lot of information. So we'll give you a lot of information. Let's go for run this one. See, if you run this one, here we are getting the R square error. Okay, 9 R square. So 95% the model is good. That means best fit model 95%, and your f value is very high, and your p value is very small. That means your model is good, and your BIC values, IIC values, it was very high. So, when I'm explaining that BIC and AIC, and so the measure the relative quality of the statistical model of the given test data, they used to balance the goodness of the FIST model, and the lower AIC and BIC were indicating that better models. See, if you see these values, of R square and register R square and F value, we cannot concluding that my model is good. Okay, here we have the BIC values, it could be little high, right? And moreover, we can see this p value. If the p value, which is the thing which is more than the 0.05, those are not much impact. So I would like to go for rebuild our my model. And your Quatrasis value, it is more than the 3. Okay, it is more than the 3. And so there could be some kind of skewness. So Quatrasis and skewness and Durbin-Watson method, Jarque-Bera method. So which are all the things will give you a lot of information. So now, I mean, here we can see p, right? Here the p is this p value is very high. Okay, this p value is very high. So this induce we can remove it, and this NYS we can remove it, and this age we can remove it, and we remove this 3, and again we can rebuild the model.
So would this get covered in statistics a little deeper as to, okay, what is this p value? What should I look for when it's the Durbin-Watson? Like what number should I look for?
Yeah.
That kind of thing.
Yep.
Okay.
Okay, so now I would like to take the training data and test data and important columns only. I'm just taking it. Okay. Yeah, I can rebuild the model, and I can rebuild the model. Before I rebuild the model, I have to train my data, right? Okay. So here, what are the features should I be considered? Here I have to remove this INDUS, right? If the p value is more, that means that is not okay, statistically significant. So INDUS, so remove this INDUS, and next, which is the p value is more? NYS. If it is more than the 0.05, NYS, remove that NYS just for testing purpose. Is there any impact on your model? Age, remove that age. Okay, you are training your we can run it. See, your 95.8, see your R square value here 95.8, sorry, 0.95.8 or else 0.958, 0.957, and F value is 691, right? So here F value was increased or decreased? F value is increased, right? So if F value is increases, that means this, when you compare with this model is little good. Okay, and this is 2467, 2472. It was reduced or not?
I think the F value is reduced, right? From 691.
691, 905.
Oh, okay. I'm sorry. My bad. I looked it
This
wrong.
is 24/2467. Here it is 2472. It was reduced. If AAC values, BAC values, little small, little change, and it was small. If smaller the AAC, BAC values, that means my model is good. Okay, you just see AAC and BAC information measures the relative quantity of the statistical model for the given set data. They are used to balance the goodness of the fit model with complexity of the model. Lower AAC and BAC value indicating that better fit of the model of the data. Okay, see, if I compare the this model and this model, I can say this model is good. I cannot say this model is good for any other model, but I'm comparing only with these two models. Okay, I'm comparing this model and this model. What is the difference between these two models? Here, some of the unwanted features I am removing it. Some of the unwanted features I am removing it. Okay, so here R square is computed without shortening, and since the model does not contains the constant, standard error assuming that covariance of the matrix of error is correlately specified, the condition of the large 2.23 that might be indicating that there are a strong multicollinearity. So this thing indicating that there could be some kind of multicollinearity. What I said in the multiple linear regression, what is assumptions we have it? No multicollinearity, right? But here it indicating that the condition number is large. Okay, is large. This indicating that there are strong multicollinearity. That means there are some of the models or some of the features are depending on the another model. Okay, so now how we can able to go for histogram with help of the histogram method, or else how we can able to check with multicollinearity. Here we have different kind of indicating that variables are highly correlated to each other. The assumption can be checked using the correlation matrix and with help of some of the visualization technique, or else we have the variance inflation factor, and within this one we have a method in variance inflation function. We have it with help of that one we can able to go for finding the VAF value. Okay. Okay, so let's go for do that one. Or else correlation matrix, we can able to go for correlation matrix. Heat map. Okay, so simply you can go with heat map Python, matplotlib. Okay. This is good. Here we have, oh, this is not good for looking. I want to look the numbers as well. Okay, this is good. I want best one. Examples. Yes, this is good. Figure. Stay connected. Okay. I want to look numbers as well. Okay, fine, no problem. So here we have a multicollinearity issue. So you should know that which variable is depending on the and which variable. Okay, if you know this one, we can remove that. We can remove instead of taking those two things, we can take it any one of it. By the time we can reduce the multicollinearity, we can overcome this particular multicollinearity issue. Okay, clear? So this is the way we can able to go for build the linear regression model. As of now, you just understood that how we can create the multiple linear regression and how we can able to kill the creating the lasso regression, ridge regression, and with help of those things, which features are important for you, which features are not important, and those things we can able to finalize it. Okay, so end of the day, what we can do with when you are applying the multiple algorithm, then from that all, so if you're able to satisfy all the assumptions, then that model is good. Okay, yep. So that's for today's session, guys, and I would like to go for upload this document, this data set. We can download, would like to go for download this one. This. I'm downloading this one. Meanwhile, the CSV file also I'm downloading it, and I can able to upload into your yes, download. Okay, just go and access your playlist. Okay, guys, that's for today's session. We'll meet.
So last one, I have one doubt.
Yeah.
Yes. Means lesser the lambda value, and more fit will be the model, and lesser the AIC and BIC value, more fit will be the model.
So I'm not talking about lambda this time. I'm talking about AIC and BIC. Okay, if the lesser the AIC BIC value, which indicating that the model is best fit model. Okay.
No, I am just asking. Means about lambda also. Before you
Yeah,
say.
yeah. About to
Yeah.
lambda, we have to take it. So that is depending on the hyper. We cannot say that small or high. Okay, but we can say that we have to apply the hyperparameter value. So lambda value is a smaller value. We can't use it like a large value, right? We can see. We can see.
Excuse me.
Like means there are 13 value. So out of these, this value is means first value is so small. I am asking that with this small value, the model will be more fit, and with this
Yeah.
last value, model will means it getting error or something.
Yeah. Yes,
Yeah.
that's correct.
And AIC and about AIC and BIC, less will be the AIC and BIC value. Means
F value should be high.
reduces, then the model will be more fit.
F value should be high. Okay. R square value, adjust R square should be high, and AIC, BIC values are small, and F start probability value of this thing, it could be the small. Okay, and the p value should be smaller than the 0.05. Okay, and this quarters is also, it could be 8, I think so. 8 is a good value, and skewness is the plus or minus 3. Okay,
Yeah.
if the data it was in between, the skewness is plus or minus 3, then that means the data it was symmetrically distributed, normality distribution, right? I already told you the data it could be normality distribution, right? That we can able to go ahead with the skewness only. Okay, and quarters in the sense there could be some kind of peakness in your data. So this all things will help you to understood the model. Okay, your Jacob JB method, and we will definitely let you know this all things in upcoming sessions as well. Okay, so this is the way usually we are able to go for build the machine learning algorithms in Python programming language. Clear?
Yeah, okay, clear.
Thank you.
Excuse me, for my work, do you have homework?
Yes.
What is the homework?
The homework is that whatever I explained for today, we have to wait. We have just to go for open that one and try to be executed. Okay.
Thank you. Bye bye.